Well, we can start now and welcome everybody to what I think is the fifth iOS Press NeuroSymbolic AI journal webinar. And my name is Eleonora Giunchiglia. I'm an assistant professor at Imperial, and today I have the really big pleasure to introduce to you Leilani Gilpin, who is an assistant professor at UC Santa Cruz. And previously, she was a researcher at Sony AI, and she completed her PhD at MIT. And today she will talk about neurosymbolic approaches for trustworthy, explainable, complex systems. And I'm really looking forward to this talk. Just before I leave the floor to Leilani, just a quick disclaimer. Today's webinar is recorded, so please remain muted throughout the talk. There will be time after the talk for questions, and so no rush. So Leilani, now the virtual floor is yours.
Great. Thank you so much, Eleanor, for that really nice introduction. I'm super excited to be here today. So I'm going to be talking about, how we can use NESI and neurosymbolic approaches for trustworthy complex systems. And when I'm talking about a complex system, I'll be talking about a system that's built out of multiple parts. I'll use self-driving cars a lot as an example. That's what a lot of my thesis work was on, but really this applies to a multitude of different systems. So let's get started. So the sort of agenda for today, so I'm going to start by motivating the problem, which is that complex systems fail in complex ways. Then I'm going to spend some time talking about a lot of the work that I've done in trying to make self-driving cars more robust, and particularly doing that by adding local sanity checks, which is basically a glorified rule-based system along with driving rules. And I'll talk about why those are also NESI approaches, because underneath that all, there's a deep neural network that's doing some interpretation of images. Then I'll talk about everyone's favorite topic, large language models. So I'll talk about how we develop tests for large language models. In particular, how do we build in logic into large language models? And I'll talk about how we've done that with different Prolog. And then finally, I'll talk about some ongoing work that we're trying to do in bridging the gap between explainable AI and neurosymbolic. And I'll try and make the argument that I think they're very synonymous. So the question I'll be trying to answer today is, how do we develop neurosymbolic methods that can help anticipate and explain failures instead of doing that after the fact? And I think that that's really important because we're seeing that a lot of these complex systems are getting into accidents and they have no way to anticipate that these things are happening. I'll start by giving a few examples of what they look like. So first, we've seen a lot of self-driving car accidents. Unfortunately, this is one of the most tragic ones that occurred just about a year ago, where unfortunately a woman was dragged by a self-driving car taxi in San Francisco. Unfortunately, the car struck them and then the person got stuck under the car and was dragged for quite a while before the car was even aware that they were there. And these are really systems that we want to feel good about, and we want to make sure that they're safe. And so we don't have a lot of safety critical infrastructure for these types of systems yet. And I argue that having neurosymbolic methods are the right way to do that. Another way that these systems fail is they fail in ways a human never would. Hopefully people can see my mouth. So this is a picture of a bus. This is an ad for some radio station here, and the self-driving car Tesla in this case thinks that this is a person crossing the street. Obviously, something that hopefully a child would be able to say that's not actually a person that's crossing the street. Now, this also happens in lots of other cases. So this is kind of small because it's taken with a phone camera. The more recent picture of a Tesla, it thinks that it's seeing a yellow light, but it's actually the moon. So failures, again, that we would never make. They are also susceptible to different types of adversarial attacks, especially in the physical world. So it's been shown with just a few pieces of tape. So hopefully everyone agrees that this is a stop sign, at least a stop sign in the US. With a few pieces of tape here, all of a sudden the self-driving car doesn't perceive this as a stop sign anymore. It actually perceives it as a 45-mile-per-hour sign, which is going fairly quickly. And you can imagine the ramifications that that causes, not just for the car that you're in, but also all the cars around it. You have an expectation that someone's going to stop at the stop sign. All of a sudden, that doesn't happen. And then finally, it's been shown that computer vision systems are better at predicting people with lighter skin tones than darker skin tones. That's for doing facial recognition. all of a sudden, when that same technology is then put on a self-driving car, all of a sudden the self-driving car is better at predicting pedestrians with lighter skin tones than darker skin tones. And so we have this multitude of different failures that occur for self-driving cars. They don't have any common sense. They're not looking at sort of higher level features. They're not aware when bad things are happening. So, how do we try and develop, safer autonomous vehicles that we can actually trust when we're inside them? And to be able to do that, we kind of have to look at where self-driving cars are, and they are largely at two extremes. So they're either, very cautious and not comfortable. This is what happened in General Motors' ultra cautious self-driving car. This is basically where the self-driving car would start and stop for anything in its way, regardless of whether that was a pedestrian or a plastic bag. So you may say, okay, well, what's the problem with that? The problem is that people who were in the car kept going forward and backwards because the car was starting and stopping constantly. And that actually gave them a false, a sense that the car was unsure. And so even though the car was safe by these means, the people in the car actually had this false sense that it was actually very unsure of what it was doing. And so what occurred with that is people said, okay, now we're actually going to have to create self-driving cars that are not just starting and stopping for anything, but actually ones that are only stopping when they're very sure of what they've perceived. And this is actually what happened in the Uber self-driving car accident, which was the first reported pedestrian fatality, largely was the topic of my PhD thesis, which I'll go over in a few slides. But basically what Uber had decided to do was they're not going to stop for any object. They're only going to stop for objects when the car is extremely sure. And unfortunately, that led to some issues as well. And so what a lot of my work has been on is how do we give complex systems better common sense and reasoning, right? They have very good, low-level data analysis techniques. Computer vision is very good for self-driving cars, so is LiDAR interpretation, but really they need a reasoning layer on top of that. And that's a lot of the work that I'm going to be talking about today. And in fact, the way that we've kind of developed that is to create models that are inspired by human organizations. And so what I've done is basically create models that are constantly communicating and constantly checking themselves. So they're constantly reporting what they're doing, and they're constantly checking that they adhere to some type of rule set. And so you can kind of think about this as having overlapping committees of people in some type of hierarchical structure. So for example, you can think about this as a software engineering team that could be here in red, and then, a software assurance team in blue that's doing quality assurance and testing. And there are a couple people in between that maybe do both. They do a little bit of software engineering and a little bit of testing. And of course, each group here has a manager, and those managers report to a higher level as well. So you can kind of think about this as the person driving the car, then you maybe have a safety system here, and then maybe you have, the vehicle tactics here. They're constantly reporting to a higher level supervisor. And then we facilitate continuous interaction and communication. And the way that I do that is with local sanity checks. So every part of the system, whether that's an individual in this sort of human analog, or every part of the system in a self-driving car, the braking, the steering, the power control, et cetera, is constantly checking what it's doing and reporting what it's doing. And actually, we have a lot of those capabilities already built into complex systems. We have the black box for things like airplanes, and we actually have a similar type of protocol for vehicles as well. All we do is add sort of a rule-based reasoning layer on top of that to make sure that they're adhering to some rules. And I'll talk about what those look like as well. And then when a failure occurs, a story can be made by combining these members' observations. So for example, if something happens, like what happened in the Uber self-driving car accident, which we'll talk about, it could say, oh, well, the vision system was unsure of what it perceived, but the LiDAR system had detected the person with enough time to stop. And basically what that's done with is with what I call an explanation synthesizer. I won't have too much time to talk about that today, but basically that looks at the explanations of different parts and then figures out which ones to trust in these critical situations. Again, very similar to the way that we facilitate argumentation as people. So if you have an expectation that your colleague is going to finish a piece of work and they don't do that, you usually have a conversation and then you come to a story of what happened that you report to your supervisor, or you give to other people on the team. And so what I argue is that with these two pieces of information, so basically a set of rules and a communication protocol, and a way to facilitate debate between parts when they might conflict, we're able to mitigate a lot of the common problems that we see in self-driving cars. The local sanity checks are able to handle what's called the trollable self-driving car, which means that there's a long laundry list of errors where they can get stuck. Some of you may have seen the newest sort of trick that people can do with self-driving cars is in San Francisco, you can put a cone on top of the vehicle and then it stops. And that's been sort of a common thing that people find to be very fun right now. And basically what we've done is we've been able to justify new examples. And then the explanation synthesizer is able to handle the sort of deadly crashes that we saw with cases like Uber and other ones as well, where that's able to reconcile conflicting reasons. And I'll also talk about a couple different ways that we actually do that. So I'll talk about how do we develop a set of driving rules to be able to justify new examples. And then I'll also talk about the use of explanations to be able to reconcile these types of conflicting reasons. So that's kind of where we're going towards today. But let me give an example of why this is very powerful. So I'm going to show here the Uber self-driving car accident. Again, this is largely what I used in my PhD thesis to evaluate a lot of the work that I did in developing these types of architectures. I am going to show the accident right before impact. I should give people a trigger warning. So this was the first reported pedestrian fatality from a self-driving car. You will see the front-facing camera. You will see moments before impact, but you won't see the impact itself. So I will kind of talk through that. It's a little hard to see because it's very dark. You'll see a person crossing the street with a bicycle, and unfortunately, they were struck and killed. So what actually happened to the vehicle in this scenario? So the vehicle had actually detected the person with enough time to stop. The LiDAR had actually detected the person long before they came through. But the problem is that they were relying on a single modality. And especially with a lot of these self-driving car technologies, it's very difficult to process LiDAR and vision at the same time. And so they just chose to ignore one. However, all of those pieces of information are extremely, extremely important. And so instead, the types of architectures that I've built are basically able to handle these types of situations. So if you're interested in how this actually works, you can read my PhD thesis. You can be maybe the fourth person to do that. But we have a very sort of simplified view of the vehicle here. So there's a monitor around the vision system, a monitor around the LiDAR system, and a monitor on tactics. And basically what we do is we create an explanation. Now I want to be very clear, this was created before ChatGPT, so all of these explanations are template-based. But of course, you could also generate them with now a generative AI system if you wanted to. We haven't integrated that yet. But the key part here is that the recommendation that it actually gives to the vehicle is based on all the different parts of the vehicle. So as I said before, the vehicle actually had enough time to stop. But it actually finds that stopping the vehicle could cause harm to the person inside the vehicle. So since there's no one around it, it actually chooses to swerve around the way. So it says that the vehicle traveling too fast to suddenly stop, that the vision system is inconsistent, but the LiDAR system has provided a reasonable and a strong claim to avoid the object moving across the street. And this is very important for a few different reasons. One is it's not doing fine-grained image detection, right? It finds that there's an object moving, and that's something that we want to avoid. And that's very important when we look at this sort of open space of risks that can occur in self-driving cars. And then the second thing is, again, it's getting information from all the different parts of the vehicle. Of course, there are more parts of the vehicle than 3 different, subsystems here, but I'm sort of showing this for demonstration facts. And so what I'll be talking about today is basically how do we create these monitors, how do we create these rules, and then how do we extend these for other systems that are not just self-driving cars. So that's sort of the introductory problem statement. So let's actually talk about how that's done. So let's talk about local sanity checks and driving rules for self-driving cars. So if we kind of think about the larger case of how complex systems fail, there are largely 2 ways that these systems can fail. The failure can either be local to a specific subsystem, or it can be due to a failed cooperation among subsystems. And that's exactly what we talked about with the sort of human organization analog. So it can either be one person as a single point of failure, or you have some expectation of people working together and it's a failed cooperation. I'm going to start by talking about the local type of failure. And in particular, I have sort of monitors built for all the different parts of the car, but we're going to focus on the perceptual mechanisms. And in particular, what I'm going to focus on is the camera data. So For those of you that are not familiar with image processing, how cameras on cars or image processing works in computer science, I apologize to people who are experts on this. I'm going to go through this in one slide, but basically a neural network will label some type of camera data. So usually what that looks like, you get some image that is passed through some type of deep neural network. And then you get some label, for example, this is a pedestrian. And this is typically what's done in the self-driving car literature. And this is still a lot of the challenges that people work on in image processing today, is basically just doing object recognition. Now, most of the time, this works really well. So for people that are unfamiliar, image processing is really at a huge peak. But the problem is that these neural networks are very brittle. And in fact, they are very brittle, especially when they see things that are outside of their training data. This has been shown with adversarial examples. So for example, this is a picture of a pig. I hope everyone agrees with that. But if you add just a little bit of noise, so 0.005 times, this noise filter to this picture, obviously you guys hope that that still looks like a pig. All of a sudden, the same network will now think that that's an airliner. Now, while that's a very cute example, we've already seen an example of this where this has already occurred. We saw this with the stop sign case, where you can actually also put these attacks into the real world. And this hasn't just been shown with stop signs. People can put different stickers on other signs and make them almost invisible for computer vision systems to see. And so one of the important things is that, although we look at adversarial examples and sometimes think that they're little tricks, for self-driving and other mission critical, safety critical applications, these mistakes have consequences. And so what we've largely done in my work is we've tried to monitor these types of opaque subsystems for reasonable behavior. And so the sort of big development that we've done is we've said, fine, great, we're just going to treat this neural network as some type of opaque mechanism. And that's actually important for a multitude of different reasons. I should say we also have some techniques for what happens when you also have access to that deep neural net, but you don't always have that. And that's for two reasons. One is that self-driving car companies are very protective over their algorithms. So sometimes we don't even know what type of model they're using. And secondly, a lot of these networks are just too opaque to understand. So even if we have intrinsic techniques where we can actually peer inside the black box, as people would say, it's not very effective. And so because of those two reasons, because sometimes these algorithms are proprietary and because sometimes they're too complex, we just decide we're going to treat them like a black box and we're only going to look at the outputs of these systems. And basically, we're going to look at this output. We will combine that with a common sense knowledge base, a flexible representation, the ability to identify what is reasonable or unreasonable, and then that will all be leading towards a justification of unreasonability or reasonability. And so the output of my system will be both a judgment of reasonableness, so to say, yes, we do believe that this is a pedestrian and here's why, and a justification of why we think that it's reasonable. And so I built, largely a sort of flexible system that does this. Again, this is taking the input of some type of neural network, and then it's representing that in a flexible way. It has a set of rules, and it's all leading to some type of explanation. It's also supplemented with a common sense knowledge base. I'm going to focus here on the sort of flexible representation and common sense knowledge base because I think that's kind of interest to the community. But I can also talk about some of the rules a little bit later as well. So the type of flexible representation that we're going to be using is largely a primitive representation. And that's largely to encode understanding. And so we're not looking at, again, low-level details like what is the specific object we're looking at, but basically what are the features that it has and what's reasonable in the domain that we're looking at. And actually, the representation we use is fairly old. So we're using conceptual dependency theory from Schenck from 1975, but it ends up working pretty well for our system. And in fact, in this proposal, there were 11 primitives to account for most actions. We focus on the 5 for physical actions because, of course, we're focusing on a self-driving car, so we're looking at the physical world. And then we also extended that to vehicle-specific primitives, so turning, yielding, et cetera. And there's a list of those that I can also talk about. So the big problem with using this type of system is we just need to be able to parse natural language into this representation. So let me show an example of how that's done. So we'll use kind of the same example from earlier. I'm showing here data from NeuroSymbolic. NeuroSymbolic is a self-driving car data set. And what they'll basically have is they'll have labels and they'll also have descriptions of what you're perceiving. So for example, this could be a woman crossing the street. Basically, what we do is we build our own in-house parser, and then we use a common sense knowledge base to try and bind both the noun, the verb, and the object into sort of higher level representations. So instead of a woman crossing the street, we want to represent that as a person moving across the street. And the reason that that's so important is because then we can represent multiple types of situations that are the same. And again, not looking at those types of low level details. And the way that we actually represent that as the conceptual primitive decomposition is with this type of representation. I can go into that more in detail, maybe in the Q&A if people are interested, but all of that means is that the person is moving, they're moving in the direction of the street, and the object doing the moving is the person. So why would we actually want to use this representation, and why does this make things, better for us? Is that these representations have implicit rules. And so this actually has the ability for us to check whether this particular type of representation is reasonable or not in our context. So, for example, someone moving is reasonable. So the actor moving towards the location here is reasonable. So X, moving towards Y is reasonable if the actor has the property that it's adamant and it's located near the location. Very simple, implicit rule. Now, of course, for this particular example, that should be fairly obvious, but what's really important for us in the self-driving car world is that for a particular frame, so for a particular moment in time that we're looking for a self-driving car, we can say that that particular frame or moment is reasonable if all of the primitives that we have in that scene are reasonable. So for example, if we have a person that's crossing the street, if we have a fire hydrant on the side of the road, and we have a skateboard that's going across the street, we have to check that each one of those primitive representations are reasonable to be able to say that we confidently believe that it's reasonable. And that's very powerful because if we see something that's out of domain, we can then alert the vehicle and we can actually learn from that experience. So let me actually talk a little bit about how this is used on real data. So again, if we look at sort of the same case here and we were to just apply sort of a basic data-driven approach. So if we weren't sort of combining the neural network approach to understanding the image, and instead we just looked at this in metadata, it's very confusing. So if you look at the data from new scenes, it has a bunch of information, but again, no higher level symbolic knowledge. You have to kind of learn that as you go. And so in our first iterations of the system, we said, okay, well, what we can do? We can just combine this with ConceptNet. We don't have to worry about having this type of representation. But the problem is that a lot of these common sense knowledge bases are unorganized. So for example, if I look up, okay, what is an adult capable of doing? If I just want to use sort of a knowledge-based approach, there's a bunch of information here that hopefully you all agree is not very related to the self-driving car world, like drinking a beer or dressing himself or acting like a child. But there are some information from these knowledge bases that are very important. For example, an adult is a type of person, it's a type of animal, and animals have certain properties, for example, that they can usually move on their own. And so part of the contribution of this system was actually to be able to use the right type of common sense data, particularly looking at only the types of relations that was important for the self-driving car world. So let's actually see some results of what this looks like. So again, we're combining a common sense knowledge base, primitive representation, and of course, the output of some type of deep neural network system that is labeling our input images. And so the monitor here will output some type of judgment and justification. So if we put the human pedestrian adult into the system, it finds that it's reasonable and it gives us an explanation why. It says, yes, this is reasonable. An adult is typically a large person. They're located walking on the street. Its dimensions is approximately the correct size in meters. So again, it's using both symbolic knowledge and it's also using some of the metadata that we were able to collect from that data set. And of course, some of the information also from the deep neural network output as well. Now, again, this works fairly well and we get these nice explanations and everybody's happy. The only problem is that I haven't shown you how it actually works for errors yet. And actually, this was one of the most difficult parts of the system. Because if you look at self-driving car data sets today, they really don't have errors built into them. And that's for good reason. One is for liability's sake. They don't want to have a bunch of, self-driving cars driving around and showing you all their failures. And so one of the big contributions of the system is we actually had to build in this data set. So we built an unreasonable image description data set. Again, it wasn't very big. We did this with 100 descriptions with different words and verbs, and had different prepositional phrases that can add additional context. And then we also built this into self-driving image processing errors. So we did real-time evaluation with Carla, that's a self-driving car simulator. And we also added errors on existing data sets like NewSings. And I'll actually show you what that looks like. One thing that we really wanted to do was look at existing errors on some of the validation data sets of some of these self-driving car challenges. Little problem with that, people didn't always release their source code, so that actually wasn't very much of a possibility, but something that we're currently looking into. So let me sort of describe what this could look like for a very, very basic error case. So I want to be clear, this is not the only types of errors that we look at, but what if this label was wrong? So what if my neural network told me, no, this is not a person, this is a traffic cone, right? Then in that case, it would say, okay, fine, this is unreasonable. And the reason it's unreasonable is because it's not a reasonable size. It's too tall, and there's no common sense supporting this judgment. And so basically what it recommends to the system is to discount objects detected in the same region. Of course, it also finds that it's unreasonable because, traffic cones can't move, but these are the most important parts that are actually shown in the explanation. So if you actually look at the reasoning process that comes out of the system, there's a lot of different rules that have been triggered, and you can look through those and do that for a diagnosis as well. Okay, so that's sort of one type of system that we've built, but let me actually talk about this in terms of sort of the larger self-driving car infrastructure that we're looking at, particularly with some of my colleagues at UC Santa Cruz. So I'm part of a big Department of Transportation center. So the National Center for Transportation, Cybersecurity and Resiliency, which is called Tracer. Alvaro Cardenas, who is an expert on security and cyber physical systems here, is the head. And you can read more about it here. Largely what my role is on the AI for vehicles front. And just so you can kind of see how the system is working in a larger, in a larger context, basically what we have is I'm working on specification. So those are driving rules, and I'm also working on the sort of end part of AI explanations. But we also have people who are working on testing the security properties, adding fuzzers, looking at adversarial machine learning and different types of failure cases, all to try and make a self-driving car more robust. So I'm going to talk a little bit about how do we develop these types of driving rules for this system. And of course, part of these driving rules are also what we built into our reasonableness monitoring system as well. I was just showing that for the image processing case. So let me kind of describe where the motivation from this comes from. Is basically, it's inspired by the way that we're evaluated as good drivers. And I know that this is done a little bit differently in the EU and the UK versus in the USA, but at least when I learned to drive, I had to basically go in and take a dynamic driving test, right? First, I had to take a written test to show that I memorized some driving handbook. And then the second thing is I had to show that I could apply those rules in a real world experience. I had to take out a car and someone had to tell me that I was a good driver. And what I think is very scary is, at least in California, at least in San Francisco, where we have a lot of fully autonomous vehicles on the road, none of that is done. If you want an autonomous vehicle on the road in San Francisco, you basically get the mayor to sign off on it, and then they can go on the road. And so what our goal is basically, can we develop a sort of set of driving standards or driving rules from text, and then use that to dynamically generate driving test scenarios? And actually, if you were sort of looking here, this is exactly what we're trying to do in this larger system. But again, I'm working more on the sort of driving rules front. So the question then is, how do we learn these driving rules from text? Well, we actually have a lot of information about that. So, each one of the 50 states in the USA has their own driving handbook. And basically what we've done is we've collected all of those driving handbooks. We've sort of filtered that to only look at the chapters that depend on safety. And then we do both manual and automatic extraction to create different rules that we represent in both RDF and in natural language. We then validate them, so we refine them and make sure that they're relevant, and then we do some analysis, so both manual and automated analysis. So one of my students is really interested in how do driving behaviors look different across different states. They're also interested in how they look different across different countries. So how are driving rules different in places like Australia versus the US or versus the East Coast versus the West Coast. So we're also doing that type of analysis. But let me show you a little bit about what the rule representation looks like and why this is, something that could be interesting to this community. So again, we have this sort of driver handbook, and basically we go through the safety chapters, and then we represent them in these basically RDF variant of rules. So what you can see here is that, you might have a pedestrian rule here that's basically saying, don't get into the path of a pedestrian. And what's really nice is we actually have a description here. This is a very short one, but this can also form part of an explanation. And with a production level reasoner, you can actually backwards chain this, and you can do different types of inference. The other really nice thing is, because these are web rules, you could actually share these amongst vehicles. So if we have vehicle to vehicle communication, you can tell the car next to you, hey, these are my constraints. What are yours? I want to make sure we're kind of agreeing on those things. And that could be a really nice way to kind of ensure safety. Now, of course, we don't have that right now, but that's kind of a dream of mine. But this is what our representation looks like. Let's actually talk about how this can help us identify some of these out-of-domain safety cases. So I'm just going to show a couple of the individual rules that we've been able to uncover. There's a long list of them, and they're publicly available on GitHub for anybody that's interested. So, one rule that was found was for particular states in the Midwest, where there's a lot of dust storms and other things. If the car, so self, that's referring to the vehicle you're in, if it encounters a dust storm, then you want to reduce speed. So why is that important? Because autonomous vehicles can get weather reports and correlate to camera feed and then adapt their driving behavior. Again, this is something I didn't even know because I haven't seen a dust storm in California yet. The other thing they can have is, for example, it can look at different anomalous situations. So, for example, if there's a car with a trailer, then that can cause a jackknife. So a jackknife is basically where the car, or at least the back part here, is kind of on one wheel, and then the vehicle is turning the other way. And this is important because autonomous vehicles can then identify if they're pulling up to a trailer, and they can drive accordingly. Again, I think this is something that a lot of us learn through driving. At least when I started to learn, if I was near a truck, I would drive a certain way. But these are important rules to kind of validate that type of behavior. Cool. So that was kind of the sort of overview, again, of the type of work we're doing for self-driving cars. But let me talk about, maybe a little bit more of a exciting area, or maybe a little bit more mainstream. So let me talk about how we do the same type of thing, but for large language models. And in particular, I'm going to talk about how do we incorporate different types of logics into large language models. So the problem with this is that, and it should be no surprise, large language models, they're opaque and they produce false information. And if this is news to you, I apologize to be the person that's bringing this up. But so what do? Well, they hallucinate. Their reasoning process is not transparent. They're not explainable, kind of. I'll get back to that, but they're not interpretable. You can't trace their decision. And there have been a lot of previous solutions, but they haven't worked super well. So there are all different types of techniques that people use to kind of mitigate this type of behavior, whether that's chain of thought, so different types of prompting techniques, or retrieval augmentation, getting better information and then incorporating that in, or even using post-hoc explainability. And I'm going to talk a little bit about post-hoc explainability because that's something that we've looked at in my group. But actually, if you look at explanation methods for large language models, they're not trustworthy. So we wrote this paper with a colleague of mine from MIT. And what we found is that, yes, LLMs can explain themselves. And some of you may have seen this before, is that you can ask them, why did you get to that answer? And so what we did is we looked at some of these large language model self-explanations on movie reviews. So looking at sentiment analysis of movie reviews, is this positive, is this negative, and can you tell us why? And we examined some of the feature attribution. So we looked at the actual word scores. So which words were actually important to that output. So either being positive, negative, or neutral. And then we validated these explanations with different explainability metrics that we know well. So comprehensiveness, sufficiency, rank correlation, and many others. And if this is all jargon that you don't understand, no problem at all, because this is the big takeaway. The explanations are not faithful. And this should be no surprise to anybody. But what the large language models are telling you with their self-explanation, so when they're explaining to you how they got to their reasoning, that's not faithful to how they actually got to that output. They are just telling you what they think you want to hear. Um, so we can't really trust these types of self-explanations. And so basically that led us on a slightly different path, which is that how could we instead not trust the self-explanations, but maybe refine different LLM outputs? And so basically what we've been doing is trying to maintain a domain-specific knowledge base with rules for a large language model. And that set of rules can be augmented through experience and expertise, and that can also have different types of time-sensitive information. And the reason that this is important is, again, largely this is very similar to the type of reasoning that we do, and it's very analogous to what I showed in the self-driving car case. All that we're doing now is we just have a knowledge base and a set of rules for a specific large language instance for a particular user. And I'll kind of show this process through a running example. So the running example that we use is we actually started this system because we were trying to create a UC Santa Cruz specific chatbot. And we were interested in some of these, silly questions that undergraduates will ask when they come to campus. For example, how many dining halls are there at UC Santa Cruz? And if you ask ChatGPT now, this is probably, 6 or so months ago, it would tell you that UC Santa Cruz has 3 dining halls, and it would tell you which dining halls they are: Cal Stevenson, Crown Merrill, and College 9, right? Now, you don't even have to be an expert at UC Santa Cruz, but I'll give you some statistics also to maybe plug NESI 2025. But UC Santa Cruz is a fairly large public university, and we have about 19,000 undergraduates. And so I would ask you if you think having 3 dining halls is going to be enough for 19,000 undergraduates. Hopefully the answer is no. But if you kind of look at this, this is clearly wrong. You could do that by either looking at the Wikipedia of UC Santa Cruz. You could do that looking at the information online, or you could just use common sense and say there are way too many students. There's no way that 3 dining halls could serve all these undergraduates. So how are we basically going to fix this? Well, we're going to build in different sanity checks. As I said, you can look at the sort of dining halls here and you see, oh my gosh, there are much more than 3. There are 1, 2, 3, 4, 5 dining halls, as well as several other places where you can eat on campus. And so basically what we did is we said, okay, what we're going to do is we're going to kind of standardize this type of information, similar to what you would see with retrieval augmented generation, but we're going to do it with logic. Yay. So actually what we did is we used the LLM to be able to generate actually Prolog for us. And again, what's nice with Prolog is it has different types of provable properties, and we can do all the different types of chaining. And actually, LLMs do a remarkable job of generating this type of Prolog. So that was kind of our big takeaway. Anyway, it works pretty well. We're still working on how do we actually validate that the Prolog is correct. And if people have ideas for that, would love to hear some people's ideas there. So let me sort of describe now. We have this information. How does this actually work in a larger system? So we're basically using logic to form this type of chain of thought. So we divide the task of answering questions into these different parts. So every question needs facts or contextual factors to answer on. That's the sort of logical part. And then the reasoning behind gathering those facts, also logic. And then the reasoning over these facts to form the final answer. So basically, we take a large language model, we get the facts that we need from some type of database. We have them translate that to Prolog. We do some inference on the Prolog. Then we say, hey, can you take that Prolog and generate that back into natural language? And that's exactly what you see in kind of our system diagram. So you get some user input. You have a neural translator that turns that into Prolog queries. We basically do some symbolic components. We're doing some queries here, some reasoning. We get the truth value of every query, and then that's then passed to the user. So there's a little sort of monitor inference layer here that's basically checking all that information. And of course, the sort of neural component, again, is here at both ends. I'll just sort of briefly go through this just for sake of time. We kind of have this for 2 different use cases. So the biggest one is for fact checking. So for hallucination detection and explanation, where we're going to backwards chain to the query. So basically we can prove that our output is truthful or not. But you can also use this for user personalization. So you can develop a user specific knowledge base and again, use the same type of process, but you can keep track of that knowledge base and constantly update that for individual users, which is really nice. So, for those of you that aren't familiar, backwards chaining, it basically builds a proof and, what we're hoping is also trust. It's appropriate for this type of problem solving. You can use it for, high level things like where are my keys? How do I get to my next class? And what's also nice is, unlike forward chaining, it can actually be much less than linear in the size of the knowledge base. So it actually works pretty quickly. And it creates a goal tree or a proof, and it's interpretable and understandable. So let's sort of recall our two use cases, and I'll show a couple system diagrams of how this actually works. So the fact-checking workflow, very similar to what we saw before. So the user has a query, then we get the prompt, the history, and the user query, which is passed on to the neural generator to get the large language model response. That's then converted to Prolog. We do some symbolic component inference here, and then that's eventually passed back to the interface, and that's translated into natural language to the user. We have a very, very similar workflow for these sort of user personalization. The only difference here is that now we're not just getting the sort of knowledge-based information, we're also getting some context specifically from the user that we're looking at, and then that is passed back to the interface as well. The current sort of domain that we're working on, again, is looking at UCSC specific queries. And the reason we're doing this is because I'm working with a large group of students here, and they immediately know the right answer. So they're the sort of the best validators of this type of system. And the web information is available, but it is consistently wrong. So the kind of example that I usually give to students, and maybe this also rings true with a lot of other people. So I'm a big avid swimmer, and the pool hours are never correct on the website. And I will walk across campus only to find that the pool has been closed. And so it would be really nice if we could actually use this type of system to basically update information as we go. So to say, oh, actually, another user from the system just said that the pool was closed, you probably shouldn't go there right now. And so, we're also thinking about this for other domains as well. So one of the places where a lot of ChatGPT queries fail are for things like individual biographies. So I'm sure if many of you guys have asked ChatGPT about yourself, it will say and hallucinate different information. Like until recently, I think it said I was a professor at University of British Columbia, which is not true. Another case that we're looking at, which we're really excited about and trying to incorporate in, are looking at medical case studies. So particularly looking at medical case studies that have come out after the large language model has been trained. And we know when those cases are, especially for things like ChatGPT. And so we're looking at how we can actually represent those. We're collaborating with some emergency room doctors at UC San Diego on this topic. Okay. So just a little sort of demonstration again, how this works for a very, very simple example. So we have sort of a neural translator, and let's say that my student wants to know where is a quiet place that he can study. So my student, PhD student Priyesh. Okay. And basically the type of output that we'll get here is that it's looking for a place to study. We want it to be quiet and we want it to have Wi-Fi. And the particular student we're looking at here is Priyesh. The symbolic component here will return some grounded context. And basically it will output some Prolog result that will say that it's true. And it will basically say the properties that you need is that we have that it's quiet and it has Wi-Fi. And then the goal tree here is basically going to provide an explanation for this type of context. And again, the neural translator will then be converted to natural language. So we have to find a place that's quiet and we have to have a place that has Wi-Fi. And if we have that information in the knowledge base, it will say, okay, you can go to these 3 libraries that also have Wi-Fi, and we know that they're quiet. So where are we kind of taking this next? The next thing that we're really looking at are what if the facts are not in the knowledge base? We've been very lucky because we've been looking again at UC Santa Cruz specific queries that we can kind of get all this type of information. So some new integrations we're working on are asking users for their preferences and storing them as new rules, which will basically help the dialogue system be self-learning. One thing that we're also looking at are ways that we can actually use a large language model to update and write new rules for us. We're a little bit skeptical of that because we found that they're not very trustworthy. So again, one of our big issues with these types of technologies are the evaluation. So if we're using, some type of generative AI, some type of neural system to be able to generate symbolic parts for us, we have to be able to trust that those things are right. We haven't had that so far. So just to sort of tie up things, let me talk about some ongoing work, where things are going, and then hopefully that will facilitate some discussion at the end. So, I sort of started this talk with this idea that complex systems, they largely lack common sense. They can't do the same types of things we want to do. And what I argued is, a way to check for this common sense is to basically have some type of explanation. And I've spent a lot of my career thinking about what makes an explanation an explanation. But I think for us as kind of a community, one of the biggest issues is that these explanations are largely static. And what we need are more dynamic explanations under uncertainty and really self-explaining architectures, that the explanation is not really, the end excuse, but the explanation is constantly changing as different information is changing. And I argue that a lot of the architectures that we're building in this community actually have those types of properties. We just need to figure out the best way to communicate that. And I kind of have a couple different ideas of how we can do that. So this is creating, complex systems that are articulate, that actually coherently communicate, one, with other systems, but also with us, right? What I've largely talked about today is the way that you can have some type of neural network and you can pass that into a symbolic system, right? But what if they actually communicated together? And I know there are lots of people in this community that are thinking about that. And what I argue is that explanations could be that common language to actually complete these tasks. This is important for redundancy because systems solve problems in multiple ways. We know neural nets are very good at some things, symbolic systems are very good at other things. But also important for hybrid processes so that systems can learn from each other. Again, we know that symbolic systems are good at some things and neural nets are good at other things. Can they actually pass knowledge back and forth? This is also important for communicating with humans. I argue that explanations are a debugging language. I also do a lot of work on AI in education and particularly trying to develop explanations to communicate better with students. This is important for debugging so that humans can improve complex systems and we can actually understand what they're doing. But also, in the educational context, that complex systems can improve or teach humans. And this is very important, especially in the medical domain. It's been shown that a lot of neural network-like systems are better at doctors at predicting different types of anomalies. For example, in breast cancer, a lot of deep neural networks are better at predicting small indicators than doctors alone, but we don't always know why. So can we actually develop explanations on top of these systems as sort of a symbolic layer to be able to communicate better with humans from a complex system? So, how are we going to get there? Right? Again, I sort of argue a lot of this is with common sense. I'm sure many of you guys have seen the hype cycle for artificial intelligence. You'll see that knowledge graphs and autonomous vehicles are here in the trope of disillusionment, right? But I would argue, are we really there? We still have autonomous vehicles that, can't, tell whether this is the yellow light or the moon, right? However, we actually, with a very simple knowledge graph, it gives us the answer. We just need to have that integration, right? So I think that we're actually pretty close to getting there. We just need to figure out, again, a way that we take a lot of these classic technologies that many of us have been developing for years and actually incorporate that in some of these new age technologies. And this is going to have an impact sort of across the field. It's important for society so that we can actually communicate with humans on shared tasks. Important for liability. A lot of my work has also been around the liability of autonomous vehicles so that systems can testify and answer questions and provide different insights. And also, for robustness for this sort of dynamic detection of failure and intrusion with precise mitigation. And so with that, I'll kind of sort of conclude. If you want more information on the type of stuff I'm doing, you can check out my lab website or feel free to write me an email or visit my website. So I sort of started by motivating this fact that complex systems fail in complex ways. I talked about a lot of the sort of rule-based systems that we can build on top of existing neural networks for making self-driving cars safer. I then talked about a similar type of technique we can use for large language models. And then I talked about how we should think about this for ongoing work in explainable AI, sort of tying that back to this sort of neurosymbolic angle. And again, we are trying to avoid these types of situations, which I'm sure many of you guys are familiar with. And I really hope that NeuroSymbolic is the type of solution to that. So with that, I thank you guys for your attention, and I'm happy to take some questions.
Well, yeah, thank you very much for your talk. Are there any questions? I personally found it very, very inspiring, and if nobody has questions, I have some. So feel free to raise your hand in case.
Or write in the chat. I can also monitor.
Well, maybe I can start if I can, if there are no other questions.
I think there are a few people with their hands raised. I don't know, Eleonora, if you want
Ah,
to people.
I don't see them. Very sorry. If you see them, just
Okay.
call one out.
Okay, sure. I'll start with I think Aditya is first on my screen. I hope I said that right.
Yes.
Hi, Leilani. Great talk. I was wondering if, for example, you had this first order logic and relations and so on between. But what about dynamical knowledge, like models of the world and this kind of stuff? How can those be incorporated? That was.
Oh, absolutely. I mean, we are thinking about other types of temporal logics and other things as well. We've focused on the first order logic because largely we're trying to do like diagnosis, find the single point in time where that's going to fail. But you're absolutely right. I mean, this won't handle different types of like time variant information. And actually, this is something that my colleague and I are working on. So Daniel Fremont has a formal verification system called Scenic for self-driving cars, and that relies on a temporal logic. The one thing we're actually trying to do is to try and translate some of this stuff into basically a modal logic, but we haven't gotten very far yet. Unfortunately, my students don't have well, I feel bad if they're watching this recording, but we don't have a logic class here. So they're working very hard, but it's taking a little bit. Awesome. I think next is Bertram.
Yeah.
I'm sorry if I said that wrong.
Yes, thank you. Fascinating talk, wonderful. Glad, I don't know where I saw it advertised, but I'm glad I found it. Yeah, I'm sort of a old-time logic programmer, sort of the old AI, and it's wonderful to see how it comes together with a new AI, generative AI, and so on. My question is sort of somewhat similar to Aditya's, I think, in the sense that there are other sort of more declarative languages out there than Prolog. I'm a Prolog programmer myself, so I enjoy doing that. Because of that, I know its limitations. And another paradigm, for example, that I use in research and to lesser extent in teaching, not a lot of people learn logic these days. I think that's what you're also experiencing. That is answer set programming, sort of a more declarative way to reasoning. So, anyways, I was just throwing it out whether you're already thinking along those lines or whether that is something possibly of interest. It has its own disadvantages. All these systems are kind of difficult to engineer. Anyways, thank you.
No, so absolutely. That's actually so. I'll actually tell you the reason that we chose Prolog, and maybe it's not the best one, but one was because I've done a lot of Prolog, and a lot of the verification of my thesis was in Prolog, so a bit of it was selfish on my part. The second part is we actually had a set of students try and look at what types of logics large language models were good at generating, and Prolog was by far the best. And again, that's not a perfect reason, but it made it so we could actually kind of bootstrap and build this system. But I agree. I mean, I would love to look at answer set programming or different types of modal logics. Yeah, it's been out there they have 50 years of training data. They know what they're doing. And actually, it does pretty well. But yeah, no, we would love to extend this system to other types of symbolic and logical approaches. Again, the difficulty has just been on the translation of natural language into these types of logics, which I'm sure is a difficult question for all of us. So. maybe I'll answer maybe one from the chat, and then I'll go back in person. So Jaber, I apologize if I said that wrong. You mentioned knowledge graph at the end of your presentation. Any reason you preferred Prolog over knowledge graph? So one of the reasons we preferred Prolog, at least for the sort of large language model case, was again because we could easily translate that from the query itself, from the query and the answer easily into Prolog. And one of the problems that we found with the knowledge graphs that we were looking at were that they were very noisy and they didn't always get to the right answer. And of course, you'd want both. And we kind of showed how we did that in the autonomous vehicle problems. I didn't go over that, but we kind of weeded out the knowledge graph information we didn't want. but yeah, for us, again, it was kind of to bootstrap a system for looking at validating different answers. But I totally agree. A more ideal system would have both. So well, maybe next we'll go to Patrick.
Yeah, can you hear me?
Yep.
Yeah, very nice talk. I just wanted to ask, so I understood one of the reasons of using logic is also explainability.
Mhm.
And in Prolog, you use these goal trees or proof trees.
Yeah.
How do you use them then? Do you just show them to the user, or do you transform them in a more user-friendly format?
Yeah, so right now we just show them to the user, and I have to say that's actually not straightforward because we have to have a way to basically take the Prolog and then turn that into LaTeX, which turns that into a graph to show to the user. And so far we haven't done a large scale user study so I can't tell you how much users like them right now. I can tell you that the system experts that we've shown are very satisfied.
Yeah.
But yeah, so right now we've just used them for showing them to the user. I think eventually we would want to take that and turn that into natural language. And we do for the answers, but we haven't actually used the goal tree structure yet. But that's also because we haven't gotten a super complicated query either. Usually the types of questions that we get in these systems are, where are things located, or is there a power outage on campus? So it's usually just, a 2 or 3 layer goal tree. But I think as we get to more complicated queries, you're exactly right. Like we might want to translate that back into some type of natural language explanation. But right now we're just looking at the goal tree.
There's a question of whether when you have a very large goal tree, whether transforming it into natural language makes it more understandable.
Yeah, so that's also a very, very interesting question. So I did a study years ago that never got published, unfortunately, that was looking at the size of not goal trees, but at decision trees and how users trust them for explanation. So obviously, well, I don't know if it's obvious, but decision trees can be universal approximators, right? You can make an infinitely long decision tree that will explain any decision. And it should be no surprise that users preferred smaller decision trees that were less accurate as a good explanation. And so I think there's absolutely this type of trade-off, but then there's also like the goal tree also gives certain pieces of information that you wouldn't naturally get in natural language. I'm sorry, I used naturally twice there. So I think there's an interesting trade-off that would be really interesting for people to study. I don't do a lot of user-centric research myself, but if anyone's interested in collaborating who does, I would be thrilled. So
Okay, thank you.
cool. Now I get to show how bad I am at names. Is it Ole? O-L-E? Did I say that right?
Yeah. First of all, a big thank to you for your great and interesting talk. But I've wondered about some specifics about your LLM logic topic.
Mhm.
So you mentioned a couple of times the neurotranslator, which translates the natural language into Prolog queries and vice versa.
Yeah.
And my question would be, how did you train these neurotranslators? Or is there something pre-trained you just simply used? Or what did you do there? Or did you use the LLM itself to translate it to Prolog? Or
Yeah, so right now a great question and glossed over it for a reason. So right now we just use the LLM. We haven't used a specialized pre-trained network, but we want to. And again, part of that is, just sort of bootstrapping this application together. but yeah, right now we've just used the large language model. And again, we call it the neural translator because eventually we'd want it to be some sort of type of fine-tuned thing that's verifiable. But yeah, right now we're using the same type of LLM and we don't have a good evaluation of how good that translation is. So we'd absolutely, love to have our own in-house translator, but we haven't done that yet.
Okay, yeah, thanks.
Cool. Next I'll go to Gary.
Yes, you speculated about the role of explanations as communications, useful communications between the symbolic and the non-symbolic systems. Yeah, and you also talked about dynamic explanations. I tend to think of some of that as hypotheses that systems might be engaging. And I also wondered whether, as a higher level structure for this, you might have considered something like the belief, desire, intention type of architectures, so that systems have certain beliefs and they're doing something with intentions, and you might have that as a controlling mechanism.
Yes, I have absolutely considered this. I think this is part of the yeah, I have absolutely considered this. I think it's been a little bit difficult again for me to get students to work on this because some of these techniques, as a lot of you guys have seen, are slightly older. And a lot of students, part of the reason this LLM project came is because people said, oh, I want to work on LLMs. And I said, well, I don't really do that type of stuff. And they said, oh, what if I could add logic on top of it? I said, oh, okay. Yeah, but I do think that the BDI systems could be very powerful here. I haven't seen a whole lot of work on that, but I would love to explore it. I have to be honest, I don't know as much about them as I probably should. But I mean, that was absolutely a consideration. We were looking at different, especially with some of the vehicle rules, we were looking at different hierarchies of needs and other things for a while, but didn't eventually go that far. But yeah, I think there are lots of different higher level representations that we could consider. We haven't had the timer or
I saw that you tapped into Shank's older work.
Yeah.
There's a bunch of us who worked on AI back in the 80s and earlier that sort of growl about the fact that some of the things that people talked about then could be used now and sort of being ignored.
Exactly. No, I mean, I am all with you. I think it's again, it's been very hard for me to convince students that this is the right thing to do, right? Also because I'm also a little bit younger, but I love AI and computer science history, so that's been a lot of my goals. But I think there's a need, right? Like you were saying, like all of these representations that I've talked about are things people have already developed. They just haven't been used in the modern AI sort of landscape. So I think there's a lot of room to look at those types of things.
Thank you.
Let me see. There were some on the chat. Okay. I think Gazal asked, may I ask how you found the facts? Did you add every fact as background knowledge to the system? So for the LLM system, we do that in two ways. So one is we start with some background knowledge. So we basically scraped, most of the websites that were affiliated with UCSB into the knowledge base, and you would be surprised how little information we were able to get from that. And then depending on the query, we would also go back and we'd also add specific fact information there as well. I kind of glossed through that. Again, we do that, similar to retrieval augmented generation. We just represent it basically in Prolog. Natalia asks, how is made so basically, how do you make things more scalable? Rules for is reasonable versus not rules. Great question. It's very, very difficult. And we actually had an interesting problem that I encountered during my thesis exactly with this. And this should be no surprise, especially to people who have looked at these types of problems for years. So one thing that we tried to do is obviously you can't represent, every rule with this type of system. So we tried to represent rules with experience. So basically you experience something new, you try and create a new rule out of that. And not shockingly, we got a huge rule blow up. And so we actually ended up we just represented the rule statically and ignored that for now. but I agree, we need to come up with a better way that's scalable for coming up with these different rules. And even in our driving rules that we've come up with, this sort of system, we actually had to manually go through and make sure that we didn't have like infinitely many rules for representing what a stoplight meant, right? There's a red case, a yellow case, and a green case, but that wasn't necessarily written in the text. So I don't have a good answer to that. I think it's really hard. But I agree, there has to be a better way to take care of that. And I think there's one more question in the chat from Shushma. My question is, one of the earlier set of tactics was another module aside from LiDAR. I was wondering if tactics is referring to conceptual dependency theory. Oh, no, it's not. Sorry, that's actually a very good question. Can you please explain the tactics module? Sorry, so tactics is basically the brakes, the steering, and the power control. So any part of like vehicle, and it's any part of the vehicle that's not, that's doing low level sort of motion control, but not relying on the vision or the LiDAR. And I apologize, I probably should have said that when I was talking through it. So yeah, it's braking, steering, and power control. Sorry about that.
Yeah, no, it's clear. Thank you so much. Glad to meet you again.
Yeah, you too.
Was this the last question?
I think so. If I missed one, I apologize.
I was also following, I didn't see, but maybe I'm wrong. Well, in that case, I mean,
I can ask
do we
another
have the time?
question. I can ask
Well,
another question if we have time. It's about
depends on
reasonableness.
Leilani.
Yeah. Yeah, go for it.
I have a question about reasonableness. It seems that there is a pragmatics to reasonableness in terms of likely consequences, and that a system might, certainly a human might think about the consequences of that. And I'm just wondering how you think about that or handle that.
Oh man, that is very, I wish I had a good answer for that. Now I'm going to tell all my students they have new questions to think about today. But yeah, I mean, I do think there's a pragmatic aspect. I mean, when we were thinking about reasonableness, we meant clearly dangerous when we were doing it. And again, that was because at the time when we were developing these types of systems, and partly that were constraints from the self-driving car companies that we were working on, they would say, here are some model outputs that we have, and tell us whether these are clearly wrong or not. And so that was kind of where the system came from. So, you know, it was basically like, do these violate rules of common sense? Like one like simple example we used to show that wasn't in our training set was like a mailbox crossing the street. That clearly can't happen. I mean, there's no way, right? But sometimes these self-driving cars, they will detect objects and say that they're moving, and it will be something like a traffic cone that's walking across the street, and it's a person that's carrying a traffic cone. So how do we kind of reason about those types of situations? But I agree. I think there's a really interesting question on like, what do we mean by reasonableness, or when we do these like verifiable checks, like what do those actually mean from like a knowledge perspective? But again, we haven't looked at that too much. For us, it was just like, how do we make these safer? But
The thought came up when you were talking about the car being overprotective and jerking, and there is some impact on the passengers versus the possibility of hitting somebody. So that's a classic trade-off there.
Yeah. No, you're absolutely right. Yeah, it's interesting. Yeah, I feel like there's room for especially like different levels of it, right? Like there's like, okay, like clearly unsafe, like you could, hit somebody, right? And then there's like, a little bit, a little dangerous, a little not great. Again, that kind of relates to almost we have this vehicle hierarchy, which I didn't get to talk about, of like what needs need to be met. So it's like, first you want the people in and around the vehicle to be safe. Then you want them to perceive that it's safe, right? And I think in between that is kind of reasonableness. Like you want it to be something that it's obviously safe, but you also want it to be something that's like not imaginary. But yeah, I'll have to think about that a little bit more. I have a lot of food for thought now.
I think you have one more question in the chat again, if you have the time. Everybody was very interested in your talk. It's a good
Oh, that's
sign.
great. Okay, with using RAG, you add all the documentation of the driving license to that. Am I right? I'm not sure if I understand. We didn't use RAG for the driving license part. But if we were to get a driving question from the LLM one, we would add relevant driving information from the retrieval. I don't know if that's a good answer to that question, but it also there are many different types of retrieval augmented generation, so it kind of depends on where your query is too. But sorry, I don't think that's a great answer, but
Okay. I think you answered.
okay.
Okay, well, thank you very much, everybody, for joining us today. And also, if you haven't done so and you're interested into like the neurosymbolic area, where we have an amazing Slack channel where there are a lot of things happening. So please find it and join it. And yeah, thanks, Leilani, for your amazing talk. It was honestly very interesting and inspiring.
Thanks,
Okay.
everybody.
Thanks, everybody. I hope you will have a good day or evening, depending when. Okay, bye.